So what I want y'all to do to start off is we are going to be discussing how to solve exponential and log equations. So the first thing I need y'all to understand is that they are inverses of each other. So this morning I had my first period just go ahead and do some graphing for me on their own, but I don't know if it went as well as I wanted it to. So here's what I want to do. We are going to graph this exponential function. We're going to graph the y equals x, and then we're going to graph this log function. But will you change that log function to be log base 2 of x? Every year I forget to change that. This is Miss Battles? Is this who? Yeah. Take your calculator, and I want you to type in y equals 2 to the x in y sub 1. So we're going to go to y sub 1, clear that out, 2 to the power of x. And when you graph that, you'll see that it's an exponential growth curve, but you won't be able to validate the points as easily. So what I want you to do is go to your table and pick some easy points to graph. All right, and you've got quite a few to choose from right in here to pick some easy points to graph. So notice as you go, as x is negative, that we end up with just decimals or fractions there. But your easiest one is 0, 1, at 1, 2, 2, 4, and 4, 8. I just want to, oops, wait a minute. I think I skipped one in there. At 2 is 4, and at 3 is 8. My bad. There we go. And then get your curve to go on up through there. Now, I want you to notice that we are approaching the x-axis. It is an asymptote. If you look at your table and keep going backwards, you'll notice that we keep getting smaller and smaller with the y value, but we never hit 0, but we get closer and closer. And do y'all understand how to read this right here? It looks like it's bigger, but it has e negative 4. That just really means that whatever this number is, you're moving the exponent 4 places to the left. You're making it much smaller. Okay, so it's a really, really, really small number. All right, then I want you to graph y equals x. You should not have to type this into your calculator. Remember, that's your parent function for a linear function. And it is starts at the origin, and the slope is 1. But if you want to graph it just for aesthetics, for looking, you are more than welcome to. Because why we want that y equals x graph is inverse functions reflect over that graph. So whatever points I have plotted right here, if I switch the x and the y, those are going to be my points I can plot over here for log base 2 of x. However, you might want to go into y equals and go down to y sub 2 and type in the log equation. Remember, to get a log base 2, we have to hit the math key and then arrow up so that we get log base. And then we can change that to a base of 2 and then type x into our parenthesis. All right, and then graph, and you can see that it is a direct reflection of our exponential. All right, and to get your points for it, you can go to your table of values. I'm going to, oh, looky. Why does my log function have all these errors over here for y? Can anybody explain that to me? Why would it be giving me errors? And the errors, oh, the first error started at when x was 0. There we go, because we have an asymptote. And remember, x in the log, the x value in the log, it represents, we can't log a negative number. So when x is negative, it can't be logged. And that's where we get this asymptote right here. Our y-axis becomes our asymptote. And instead of a point at 0, 1, we have a point at 1, 0. And then we have a point at 2, 1. And then we have a point at 3, 1, 2, 3, and then 1.585. So it's just a little bit higher. And it just, then we got a point at 4, 2. And then let's see, do we have another nice number at 8? We have a point at 3, 1, 2, 3. So we've got some definitive whole numbers there that we can use and see that we are growing as x is approaching positive infinity. Y is approaching positive infinity as well, but it's very slow going, very slow going. But this is what I want to emphasize here, is their inverses. Inverse functions reflect across the graph of y equals x. And whenever you are solving equations, we have to use our inverse function to undo. We use addition to undo subtraction. We use division to undo multiplication. We use exponential rules to undo log rules, and vice versa. And I want to re-emphasize this part right here. In an exponential rule, you have your base number to a power, your exponent, and it equals some answer. And if I were to take those numbers, those values, and express them as a log, our base of our exponent is the base of our log. Our answer to our exponential is what we're actually logging. And that log is representative of the exponent. Okay? And so I just have another example right here for you. So if you have a base of 10 to the second power, it equals 100. So that would be a log base 10 of 100 is equal to 2. This is what I mean. This log has to represent the exponent that we just expressed. Okay, so that's your logs and your exponents. But then we learned about this special number e when it came to continuous compounding. So anytime we have this continual growth with no breaks, we have to have an inverse for it as well. Okay, so the inverse for e is natural log. So when you see this natural log, it's because we're offsetting the e. We're undoing this e. And that's something that you're going to have to be able to identify to know when do you use natural log, when do you use a regular log. It all depends upon what's in the equation to begin with. All right? So what I want you to do is I want you to do the same thing with e and natural log that we did with our exponent equation and log base 2. I want you to go into y equals, and under y sub 1, I want you to type in e to the x. And then under y sub 2, I want you to type in natural log of x. And we're going to graph these as well. I'm going to go ahead and put my y equals x in here so that I can see the reflection. But all you need is a couple of valid points for each of those so that you can see what's going on. Do y'all remember how to get E? E is right here in blue above the natural log button. So you've got your natural log key, you've got your log key with your base 10. So you hit your second natural log, and you've got your e that shows up, and you type in x so that you've got e to the x. And then down below for y sub 2, I'm going to hit my natural log button, and in the parenthesis, that is going to be my x value. If you go to graph it, you can see each one being graphed and how they reflect each other. And if you go into your table of values, then you can go back and you can start with our e value. Notice your e value, you can have negatives, but again, we're approaching the y-axis. It's our asymptote. I'm sorry, the x-axis. That was my bad. So we've got a point, again, at 0, 1. At 1, and it's almost 3. And at 2, it's just over 7. So this rises a little more quickly than our log base 2. It's a little bit steeper of a curve there. And again, on your second equation, when we get to 0 and less than, we have errors because we cannot natural log just like we cannot log. So we now have a point at 1, 0, and we just kind of keep going. This one's a little trickier to graph. Let's see, at 8, we're at 2, just a little over 2. And then we've got our asymptote here, so you can kind of get your graph going like so. Just a couple of points to kind of get that curve going. All right, so when we're using a log, we're going to exponentiate to undo it. If we're using a natural log, we're going to use e to undo it. They will offset each other whenever we're solving equations. All right, let's take a look now at our log rules for solving equations. Just like any algebra equation, we're trying to get the variable by itself. So what we're going to be doing is getting the log term by itself, basically. We're solving for x. If you want to write here, get the log alone. So get the log term all by itself. Sometimes you might have to condense or expand in order to do this. Okay? Condensing and expanding is what we were covering yesterday, so we can't forget those rules that we were using. Then, to eliminate the log, we might have to do what we call exponentiate each side. If you exponentiate each side, you may end up with extraneous solutions and have to check them. This is not a very difficult or time-consuming process. It can be done super quickly. So I'm going to show y'all how to do that. Okay, so the first problem, we've got 6 plus 2 log of 5x equals 18. Now, if I was going to solve this, the first thing I would do is try to get that log by itself. All right? So what would be your first step to get that log by itself? We've got subtracting 6 from both sides, so we've got the 2 times the log of 5x is equal to 12. Now, let's forget about the log for just a second, and let's just say instead of 2 times the log of 5x, let's just say this was 2 times x. What would be your next step to solve the equation? Divide, right? We're going to do the same thing. We're going to divide both sides by 2. So you end up with log of 5x is equal to 6. Now, this is where we have to eliminate the log. So, eliminate the log by exponentiating by the base number. Well, what is the base of this log? 10. So that means we're going to exponentiate with a base of 10. So I'm going to, the log is going to be in the exponent. 10 is my base number, but it's also going to be my base number of the other side. So the 6 is going to become the exponent. So when I say exponentiate, what we have here becomes the exponents. This looks real foreign, okay, real different. Did y'all do this last year at all? Mm-hmm. You did do it last year. Okay. Just remember, these are inverse operations. They undo each other, okay? So now, when I take 10 to the power of log base 10, because this has a base of 10, they cancel each other out. Those operations undo each other. So I am just left with 5x. And then I've got 10 to the 6th power, which is the same thing as 1 million. And then the last step is just to divide by 5, and so x is equal to 200,000. And that is my solution. And since I exponentiated, if I plug 200,000 back in for x, I'm going to get the log of 1 million. And I'm okay. I can take the log of 1 million. It's all right. 1 million it's a real number. It's not negative. It's not zero. It will work. So I know that my answer is substantial. Okay. Does anybody have a question over what I just did? Let's take a look at example 2. All right. Notice your x is in the log, but notice that x has an exponent. What did I show y'all yesterday that's a rule that we can use to kind of expand this just a little bit? To eliminate that exponent for that x, because ultimately we want x all by itself, right? So how can we get rid of that exponent?
Put the 3 in front.
Yes, we're going to take that sucker and we're going to write it as a coefficient of the log. So this is 3 times log base 8 of x is equal to 12. I want you to notice when you do that, you can now divide both sides by 3 and eliminate that 3. So that was just a little bit easier way of getting rid of that exponent with the x. Otherwise, at the very end, we would have to take the cube root. We didn't have to do this first, but it made it a little bit easier too. So now we've got log base 8 of x is equal to 4. Okay, now how do I eliminate the log? I can exponentiate. What is my base number? This case it would be 8. Okay, because our base of our log is 8. You always exponentiate by whatever the log base is. So that cancels. You are left with just x equals 8 to the 4th power. And basically that's 64 times 64, which is 4,096, I believe. Okay. Now, I want to show you something else you could do. Okay. Because of how this is written, log base 8 of x equals 4, we could do a log roll on that if you wanted to. 8 to the 4th power equals x, and then solve for x that way. That is a possibility that you can do. I just wanted to point that out. I'm just going to exponentiate because I want y'all to get comfortable with exponentiating both sides. Will this answer 4,096 work if I plug it back into my original equation? Yeah, I can take the log of that number. It's going to be ginormous, but I can still take the log of it. okay? Because it's positive. It's not negative and it's not 0. Those are our only stipulations we got to be careful of. All right, let's take a look now on page 14. There's 2 more problems that I want to cover. The first one, we've got, I got a hole punch right through it, log base 4 of x. And now we've got 2 logs on the other side. Okay, here's the issue. We have multiple different terms with logs in them. You cannot exponentiate more than one term. And you can't just do one term and not do the other. You're throwing the whole thing out of whack. You're not balancing the equation. So what we have to do is condense this down. So what was our method that we used to condense 2 logs that were being added? We multiplied their answers right here. So this would be log base 4 of x is equal to a log base 4 of 3 times x minus 2. I want you to note that this 3 times x minus 2, the whole thing is being logged. So I'm going to put brackets around that so as not to lose anything. Now, I can simplify that by distributing the 3. So that's log base 4 of x is equal to log base 4 of 3x minus 6. Again, I'm going to group that because it could very easily get mistaken to be the log base 4 of 3x minus a 6, that it's not a part of the log. But it is a part of the log, so we want to group it in there. All right, now, I have a log on both sides. So guess what I can do? I can still exponentiate both sides with a base of what? What's the base of my log? 4. So I'm going to exponentiate with the base of 4. And those logs are canceling on both sides. You are left with x equals 3x minus 6. Now, you're just flat running solving for x. 2x is equal to 6, or x is equal to 3. And the last thing you need to do when you solve this is make sure that that 3 is valid. Okay? So by being valid, I can plug it back in for every x in my original equation. Can I take the log of a 3? Yes. Can I take the log of a 3 minus 2? What is 3 minus 2? 1. Can I take the log of 1? What is the log of 1? 0. Okay? So we're golden right here. We're good. So this is a valid answer. All right. So I didn't have time to do example 4. Let me pause this. This is where we're going to pick up.